A journey to Alpha Centauri. The Alpha Centauri system is a fascinating and complex star system located in the southern sky, approximately 4.37 light-years away from Earth. It consists of three stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, and is the closest star system to our own solar system. The Alpha Centauri system has long captured the imagination of scientists and science fiction writers alike, and has been the subject of numerous studies and missions aimed at better understanding its structure and properties. With the potential for habitable planets and the prospect of interstellar travel, the Alpha Centauri system holds great promise for the future of space exploration and our understanding of the universe. Join us as we see every aspect of this trip and elaborate on many mind-blowing interstellar travel facts. Sights of Proxima Centauri. What do we expect to see if we go to Proxima Centauri? If humans were to travel to Proxima Centauri, the closest star system to our own, there would be several fascinating sights to behold. Firstly, Proxima Centauri is a red dwarf star, which means that it has a much lower mass and luminosity than our own Sun. This would cause the star to appear much dimmer and redder than our own Sun, which emits more white light. Secondly, Proxima Centauri has two known exoplanets in the habitable zone, Proxima Centauri B and Proxima Centauri C. Proxima Centauri B is the closest of the two exoplanets and is believed to be a rocky, Earth-like planet with a mass similar to that of Earth. However, due to its close proximity to the star, it is likely to be tidally locked with one side permanently facing the star and the other side in constant darkness. If humans were able to land on Proxima Centauri B, they would experience a vastly different environment than that of Earth. The star would appear much smaller and dimmer in the sky, and the temperature on the day side of the planet would be hot enough to melt lead, while the night side would be extremely cold. However, with the right technology and resources, humans may be able to establish a permanent settlement on Proxima Centauri B, exploring the planet's unique environment and studying its geology, atmosphere, and potential for life. Another fascinating sight that humans could observe during their journey to Proxima Centauri would be the Alpha Centauri system. Alpha Centauri is a triple star system consisting of three stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B are a binary star system, which means that they orbit around a common center of mass, while Proxima Centauri orbits around them at a much greater distance. If humans were able to observe Alpha Centauri from close proximity, they would see the two stars appear to orbit around each other in a dance-like pattern. They may also be able to observe the gravitational influence that the stars have on each other and any nearby planets. Preparing for the journey. Before embarking on a journey to Alpha Centauri, scientists and engineers would need to design a spacecraft that could withstand the rigors of interstellar travel. This spacecraft would need to be equipped with everything necessary to keep astronauts alive and healthy for the duration of the journey, which could take decades or even centuries. One of the biggest challenges of interstellar travel is the distance involved. At a distance of 4.37 light-years, it would take a spacecraft traveling at the speed of light over 4 years to reach Alpha Centauri. However, current technology is nowhere near capable of achieving such a speed. Therefore, alternative propulsion systems are needed to get us there. One possibility is nuclear propulsion. Nuclear propulsion is a type of spacecraft propulsion that uses the energy from nuclear reactions to produce thrust. This technology has the potential to significantly increase the speed and efficiency of spacecraft, making it an attractive option for long-distance space travel. The basic idea behind nuclear propulsion is to use a nuclear reactor to heat a propellant, such as hydrogen or helium, to extremely high temperatures. The hot gas is then expelled out of a nozzle to produce thrust, similar to how a chemical rocket works. However, because nuclear reactions can release much more energy than chemical reactions, nuclear propulsion can produce a much higher thrust than chemical rockets. There are several different types of nuclear propulsion systems that have been proposed or developed over the years. One of the earliest designs is the nuclear thermal rocket, which uses a nuclear reactor to heat hydrogen or another propellant. The hot gas is then expelled out of a nozzle to produce thrust. This technology was developed and tested by NASA in the 1960s and 70s, but has not yet been used in a space mission. Another type of nuclear propulsion is the nuclear electric propulsion system. This technology uses a nuclear reactor to generate electricity, which is then used to power an electric engine. Nuclear electric propulsion is much more efficient than chemical rockets, but it produces a lower thrust, which makes it better suited for long-duration missions rather than short, high-speed trips. Despite the potential benefits of nuclear propulsion, there are also significant challenges associated with this technology. One of the biggest concerns is safety, as nuclear reactions can produce harmful radiation and potentially catastrophic accidents. Another challenge is the development and construction of a nuclear reactor that is small and light enough to be used in space. Overall, nuclear propulsion is a promising technology that could revolutionize space travel in the coming years. With continued research and development, nuclear propulsion could enable faster and more efficient missions to destinations such as Mars, the outer planets, and even beyond our solar system. Nuclear-powered rockets could potentially reach speeds of up to 10% the speed of light, which would greatly reduce the travel time to Alpha Centauri. However, this technology is still in its infancy and is currently not feasible for interstellar travel. Another option is to use solar sails. Solar sails are a type of spacecraft propulsion system that uses the pressure of sunlight to produce thrust. Unlike traditional rockets, which rely on chemical reactions to generate thrust, solar sails use the momentum of photons from the sun to push a spacecraft forward. The basic design of a solar sail consists of a large, reflective sail made of a thin, lightweight material, such as mylar or captain. When sunlight hits the sail, the photons bounce off the reflective surface and transfer some of the momentum to the sail. Over time, this constant pressure from sunlight can accelerate a spacecraft to very high speeds. Solar sails have several advantages over traditional rocket propulsion. First, they do not require any fuel, which means that a solar sail can continue to accelerate indefinitely as long as it is exposed to sunlight. Second, solar sails can achieve much higher speeds than chemical rockets, making them ideal for long-distance space travel. Third, solar sails are relatively simple and low-cost to build and operate, which makes them an attractive option for space missions. Despite their potential benefits, there are also several challenges associated with solar sails. One of the biggest challenges is the fact that sunlight is very weak, which means that solar sails must be very large in order to produce enough thrust to be useful. In addition, solar sails are only effective when they are pointed directly at the sun, which limits their usefulness for certain types of space missions. Despite these challenges, solar sails have been successfully tested in space by several different space agencies, including NASA and the Japanese space agency JAXA. In 2019, the Planetary Society launched a small spacecraft called LightSail 2, which successfully demonstrated the effectiveness of solar sails in space. With continued research and development, solar sails could become an important tool for exploring the solar system and beyond. Regardless of the propulsion system used, the spacecraft would need to be designed to withstand the harsh conditions of space, including radiation, micrometeoroids, and extreme temperatures. It would also need to be equipped with everything necessary to sustain human life for the duration of the journey, including food, water, air, and waste management systems. Would any amount of food or water be sufficient to survive such a long journey? The amount of food and water needed for a journey to Alpha Centauri would depend on the duration of the journey and the number of crew members on board the spacecraft. Since current technology cannot achieve interstellar travel in a reasonable amount of time, the journey would likely take tens of thousands of years, making it impossible to bring enough food and water to sustain human life for the entire trip. Assuming a generation is around 25 years, then there would be approximately 400 generations in just 10,000 years. This is a rough estimate, as the length of a generation can vary depending on factors such as culture, lifespan, and social norms. This provides us with a general idea of the timescale involved in interstellar travel, and the fact that it would require multiple generations of humans to complete, which sounds absolutely absurd. Imagine giving birth in space. Yikes. Instead, a more feasible approach would be to develop closed-loop life support systems that can recycle and reuse resources such as water, oxygen, and other essential elements needed for human survival. This approach would require a significant amount of research and development to create systems that are efficient, reliable, and sustainable over long periods. Additionally, the crew would need to rely on some form of artificial or synthetic food production technology that can create nutrient-rich food from raw materials. This technology is already in development for use in space missions closer to Earth, such as the International Space Station, but would need to be scaled up and adapted for use in interstellar travel. Launching the spacecraft. Once the spacecraft is designed and built, it would need to be launched into space. Launching a spacecraft for interstellar travel would be a monumental undertaking that would require the cooperation of multiple nations and organizations. The spacecraft would need to be launched using a powerful rocket that would propel it out of Earth's orbit and into interstellar space. Once in space, the spacecraft would need to be aligned with the correct trajectory to reach Alpha Centauri. This would require precise calculations and adjustments to ensure that the spacecraft reaches its destination. Even a small error in the trajectory could cause the spacecraft to miss its target and potentially drift off into space forever. The first step in determining the trajectory of a spacecraft to Alpha Centauri is to identify the launch window. This is the period of time during which the spacecraft can be launched with the minimum amount of energy required to reach Alpha Centauri. The launch window is determined by the relative positions of Earth, let's say Proxima Centauri, and the other planets and stars in the Alpha Centauri system, and can vary depending on the desired speed and trajectory of the spacecraft. Once the launch window is identified, the spacecraft must be launched with precision to ensure that it follows the desired trajectory and arrives at Alpha Centauri at the correct time. This requires precise calculations of the spacecraft's velocity, acceleration, and position, as well as an understanding of the gravitational forces acting on the spacecraft throughout its journey. To determine the trajectory of a spacecraft to Alpha Centauri, scientists use a combination of analytical calculations and computer simulations. These calculations take into account the gravitational forces of the Sun, the planets in our solar system, and the stars and planets in the Alpha Centauri system. They also factor in the effects of interstellar dust and gas on the spacecraft's trajectory. In addition to analytical calculations, scientists also use computer simulations to model the trajectory of the spacecraft and ensure that it is on course to reach Alpha Centauri. These simulations take into account a wide range of factors, including the spacecraft's mass, shape, and propulsion system, as well as the gravitational forces and other environmental factors it will encounter on its journey. One of the key challenges in determining the trajectory of a spacecraft to Alpha Centauri is the need to balance the energy required to reach the target with the amount of fuel and other resources available to the spacecraft. This requires careful planning and optimization of the spacecraft's trajectory to minimize the energy required while still ensuring that it arrives at Alpha Centauri within the desired time frame. To achieve this balance, scientists often use a technique called gravitational slingshotting, which involves using the gravity of planets and other celestial bodies to accelerate the spacecraft and conserve fuel. This technique was famously used by NASA's Voyager 1 and Voyager 2 spacecraft to explore the outer planets of our solar system, and has also been proposed as a means of reaching Proxima Centauri as one of the targets. Another key factor in determining the trajectory of a spacecraft to Proxima Centauri is the need to ensure that it is not diverted off course by gravitational forces from other celestial bodies. This requires careful calculations and modeling of the complex gravitational interactions that occur in the Alpha Centauri system, including the effects of the binary star system and the potential presence of other planets and asteroids. To ensure that the spacecraft remains on course throughout its journey, scientists use a variety of techniques, including course corrections, thruster burns, and reaction wheels. These systems allow the spacecraft to adjust its trajectory in response to changing environmental conditions and ensure that it arrives at Proxima Centauri with precision. The journey. The journey to Alpha Centauri would be long and arduous, lasting potentially decades or even centuries. During this time, the astronauts would need to remain healthy and alert in order to monitor the spacecraft and make any necessary adjustments. One of the biggest challenges of interstellar travel is the issue of time dilation. Time dilation is the phenomenon in which time appears to pass at different rates for observers who are moving at different velocities. It is a consequence of Einstein's theory of relativity and has been confirmed through numerous experiments and observations. During travel to Proxima Centauri, which is 4.24 light-years away from Earth, time dilation becomes a significant factor. As a spacecraft approaches the speed of light, time appears to slow down relative to an observer who is stationary. This means that time on the spacecraft will pass more slowly than time on Earth, resulting in a time difference between the two locations. To understand this concept more clearly, let us consider an example. Imagine that a spacecraft is traveling at 90% of the speed of light towards Proxima Centauri. If we were to observe the spacecraft from Earth, we would see that time on the spacecraft is passing more slowly than time on Earth. For example, if the spacecraft were to travel for 10 years, only 1 year would have passed on Earth due to time dilation. This means that if the astronauts on the spacecraft were to travel to Proxima Centauri and back at 90% of the speed of light, they would experience a total of 20 years of travel time, while only 2 years would have passed on Earth. This effect becomes more pronounced as the speed of the spacecraft approaches the speed of light, making interstellar travel seem feasible in terms of time dilation. Another issue of time dilation can be observed in GPS satellites. GPS satellites are in orbit around the Earth and are traveling at a significant speed relative to the Earth's surface. Due to this, time on the satellites appears to pass more slowly than time on Earth. This means that the clocks on the GPS satellites need to be adjusted to account for the difference in time between the two locations. Otherwise, the GPS systems would not function correctly. To mitigate the effects of time dilation, the spacecraft would need to be equipped with advanced life support systems that could sustain the astronauts for extended periods of time. It would also need to be equipped with facilities for exercise, entertainment, and psychological support to help maintain the mental health of the astronauts. Another challenge of interstellar travel is the risk of radiation exposure. Cosmic radiation is much more intense outside of Earth's atmosphere and can cause damage to human cells, increasing the risk of cancer and other health problems. Radiation exposure during interstellar travel is a major concern for astronauts and spacecraft designers. The harsh space environment, which includes cosmic rays, solar flares, and galactic cosmic radiation, can cause serious health problems for humans and damage critical spacecraft components. Another strategy is to design spacecraft that are more resilient to radiation. This can involve using radiation-resistant materials for critical components, such as electronic systems and power supplies. Additionally, spacecraft can be designed to have redundant systems that can compensate for failures caused by radiation. One of the most effective strategies for mitigating radiation exposure during interstellar travel is to limit the duration of the mission. The longer the mission, the greater the exposure to radiation, and the higher the risk of health problems for the crew. By designing missions that are shorter and more efficient, spacecraft designers can minimize the risks of radiation exposure. In addition to these strategies, astronauts can also take measures to protect themselves from radiation exposure. This can include wearing radiation shielding garments such as lead aprons or vests, and taking medications that can reduce the risk of radiation sickness. Astronauts can also monitor their radiation exposure levels and take measures to reduce their exposure, such as by staying in shielded areas of the spacecraft during periods of high radiation. The spacecraft would also need to be designed to be as self-sufficient as possible, as resupply missions would be impossible given the distance involved. This means that it would need to generate its own power, recycle its own waste, and produce its own food and water. During the journey, the astronauts would have plenty of time to study and observe the universe around them. They could conduct experiments, take measurements, and observe distant stars and galaxies. They could also communicate with Earth, sending back data and images of their journey. Arriving at Alpha Centauri. After potentially decades or even centuries of travel, the spacecraft would finally arrive at Alpha Centauri. The most interesting target would be Proxima Centauri. The spacecraft would need to be equipped with instruments for studying the star system and its planets, as well as equipment for landing on the planets if they are deemed suitable for exploration. The star system consists of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B are similar to our own Sun, while Proxima Centauri is a smaller, cooler star. Proxima Centauri has an Earth-sized planet in its habitable zone, known as Proxima B, which could potentially support life. If Proxima B is deemed suitable for exploration, the spacecraft would need to be equipped with a lander capable of safely landing on the planet's surface. The astronauts would then need to explore the planet and collect samples for analysis. The first step in planning a landing on Proxima B is to gather as much information as possible about the planet's surface and environmental conditions. This requires a combination of telescopic observations, remote sensing, and in situ measurements. Scientists need to determine the composition and topography of the planet's surface, as well as the atmospheric conditions, temperature, and radiation levels. This information is used to design a landing system that can safely navigate and land on the planet's surface. Once the necessary information is gathered, the next step is to design a spacecraft and landing system that can safely reach the planet's surface. This requires a combination of propulsion systems, guidance systems, and landing technologies. The spacecraft must be able to navigate the complex gravitational forces and other environmental factors in the Alpha Centauri system and make any necessary course corrections along the way. One possible landing system for Proxima B is a descent module, similar to those used in the Apollo missions to the Moon. The descent module would detach from the main spacecraft and use its propulsion system to slow down and land on the planet's surface. The module would need to be designed to withstand the high temperatures and pressures encountered during atmospheric entry and landing, as well as the potentially harsh conditions on the planet's surface. Another possible landing system for Proxima B is a rover, which would allow scientists to explore the planet's surface in greater detail. The rover would be carried to the planet's surface by a descent module and would be equipped with a range of scientific instruments, such as cameras, spectrometers, and drills. The rover would need to be designed to withstand the harsh conditions on the planet's surface, including the potential for high radiation levels. Regardless of the landing system used, the spacecraft must be able to land on the planet's surface with precision. This requires precise calculations of the spacecraft's trajectory, as well as an understanding of the complex gravitational forces and other environmental factors in the Alpha Centauri system. Scientists use a combination of analytical calculations and computer simulations to ensure that the spacecraft lands safely and accurately on the planet's surface. Once the spacecraft has landed on Proxima B, the next step is to conduct scientific experiments and explore the planet's surface in greater detail. This could involve collecting samples of rocks and soil, analyzing the composition of the atmosphere, and searching for signs of life. The data collected from these experiments would be critical in understanding the potential habitability of the planet and the prospects for future colonization or terraforming efforts. How far can we know about the exoplanet hosted by Proxima Centauri? The James Webb Space Telescope will be able to analyze Proxima B's potential to retain an atmosphere as it orbits its star. From Earth, Proxima B will go through different phases, much like the Moon, and JWST's infrared view will be able to detect the combined brightness of the star and planet, which will likely alter in a sinusoidal pattern throughout the exoplanet's 11-day orbit. An atmosphere-free body experiences drastic temperature fluctuations. The illuminated side of the Moon can reach 117 degrees Celsius, while its dark half is kept at minus 179 degrees Celsius. On the other hand, an atmosphere helps to spread heat. Day and night temperature disparities on Earth might be as small as a few degrees. The data could serve as a valid indication of atmospheric thickness. An atmosphere as thin as that on Mars would not balance temperature like a denser atmosphere like Earth's. Light reflected off Proxima B's surface could pass through a hypothesized atmosphere and give insight into the gases present. However, because Proxima Centauri is much brighter than its planet, Proxima B's reflected light is overpowered. To uncover the planet's secrets, astronomer Ignace Snellen and lovers of the University of Leiden discovered a two-part system that can be used at the Very Large Telescope, VLT. The researchers will utilize spectropolarimetric high-contrast exoplanet research, SPHERE, an advanced adaptive optics instrument, to correct for the disturbance caused by Earth's atmosphere to telescopic images. This could make the star and planet appear much clearer, decreasing the contrast to 1,000th of the original level. Instead of having a planet that's 10 million times fainter, we will have a planet that's 1,000 times fainter. ESPRESSO, which stands for Échelle Spectrograph for Rocky Exoplanet and Stable Spectroscopic Observations, can separate the light from Proxima B from the starlight of Proxima Centauri by detecting the Doppler shift. This phenomenon occurs when the radiation emitted by a moving body changes its wavelength, becoming longer when traveling away from the observer and shorter when closer. ESPRESSO can pick up the subtle difference between the two lights, paving the way for astronomers to analyze the planet's molecular composition. The presence of biosignature molecules like oxygen and water vapor could provide exciting discoveries. The VLT could spot light variations in reflectivity as Proxima B rotates. If the planet has oceans, they would act like mirrors and cause a noticeable glint. To make this happen, upgrades need to be made to SPHERE and ESPRESSO, such as a new coronagraph for SPHERE and an optical fiber link between the two instruments. Scientists believe they will be able to discover Proxima B's composition and surface features in the next 3 to 5 years. Otherwise, if Proxima B is not suitable for exploration, the spacecraft could continue on to explore other planets or asteroids in the Alpha Centauri system. Video games on Proxima Centauri. As we already established that going to Proxima Centauri is difficult due to the distance, the energy requirements, time dilation, radiation exposure, and many more challenges that we discussed earlier, why not go there yourself behind the screen of your computer? Did you know you could explore the universe through video games? Starpoint Gemini Warlords is a space exploration and combat game that allows players to visit the Proxima Centauri star system, as well as a variety of other fictional star systems. In the game, players take on the role of a space captain and must navigate their ship through a variety of different environments, including asteroid fields, gas clouds, and space stations. One of the most exciting features of Starpoint Gemini Warlords is the ability to visit and explore the Proxima Centauri star system. This system is home to several planets and moons that players can visit and explore, each with its own unique terrain and environment. One of the most interesting locations in the Proxima Centauri star system is the planet Proxima B, which is located in the habitable zone of the star and has the potential to support liquid water on its surface. In the game, players can land on Proxima B and explore its surface, which is depicted as a harsh and rugged landscape with steep mountains, deep canyons, and volcanic activity. In addition to exploring Proxima B, players can also engage in combat with other ships in the system, either by engaging in dogfights or by launching missiles and other weapons. There are also several space stations and other points of interest in the system that players can visit and interact with. Overall, Starpoint Gemini Warlords offers a fun and exciting way to explore the Proxima Centauri star system and learn more about the potential for life in other star systems. While the game is not a scientifically accurate depiction of the real Proxima Centauri system, it does provide a fun and engaging way to learn about space exploration and the challenges of navigating through space. Another video game that would take you to Proxima Centauri in seconds is No Man's Sky. No Man's Sky is a procedurally generated space exploration game that allows players to visit a vast number of different star systems, including Proxima Centauri. In the game, players take on the role of a space explorer and must navigate their ship through a variety of different environments, including asteroid fields, gas clouds, and space stations. One of the most exciting features of No Man's Sky is the ability to visit and explore the Proxima Centauri star system. This system is depicted as a vibrant and colorful environment with several planets and moons that players can visit and explore, each with its own unique terrain, environment, and life forms. One of the most interesting locations in the Proxima Centauri star system is the planet Proxima B, which is located in the habitable zone of the star and has the potential to support liquid water on its surface. In the game, players can land on Proxima B and explore its surface, which is depicted as a lush and vibrant landscape with a diverse range of flora and fauna. In addition to exploring Proxima B, players can also engage in combat with other ships in the system, either by engaging in dogfights or by launching missiles and other weapons. There are also several space stations and other points of interest in the system that players can visit and interact with. One of the most unique features of No Man's Sky is its procedural generation system, which creates a virtually infinite number of different star systems, each with its own unique sets of planets, creatures, and resources. This means that no two trips to the Proxima Centauri star system will be the same, and players can continue to explore and discover new things even after they have visited the system multiple times. Overall, No Man's Sky offers a fun and immersive way to explore the Proxima Centauri star system and learn more about the potential for life in other star systems. While the game is not a scientifically accurate depiction of the real Proxima Centauri system, it does provide a fun and engaging way to learn about space exploration and the challenges of navigating through space. A journey to Alpha Centauri would be one of the greatest accomplishments of human exploration. However, it would require a tremendous amount of resources, technological advancement, and cooperation between nations and organizations. The journey itself would be long and arduous, lasting potentially decades or even centuries, and the astronauts would face numerous challenges, including time dilation, radiation exposure, and the need for self-sufficiency. Nonetheless, the potential scientific discoveries and knowledge gained from such a journey could be invaluable to our understanding of the universe and our place in it. Furthermore, a successful mission to Alpha Centauri would also open up new possibilities for human colonization and exploration beyond our own solar system. It could inspire future generations to continue pushing the boundaries of human exploration and discovery. In addition to the scientific and technological benefits, a mission to Alpha Centauri could also have significant cultural and social impacts. It would require international collaboration and cooperation on an unprecedented scale, bringing together people from different countries, cultures, and backgrounds to work towards a common goal. These benefits, along with the potential for new discoveries, make a mission to Alpha Centauri a highly attractive prospect. The journey would likely be long and difficult, but the potential rewards are immense. With the right combination of technology, knowledge, and determination, it is possible for humans to reach the stars.